So after having gone through these primary learning objectives, there are 2 or 3 great opportunities to extend the DIY receptive field as a final project. We put a couple of elements at the bottom of the project that should point you to, how to assemble this type of understanding in something more complex. But one of them is a fundamental problem of neural networks and the reason why connectionism died in the 70s. Anyone knows why that would be? Anyone has ever stumbled upon the XOR problem? And anyone knows what an XOR is? Anyone knows what an AND logical operation is?
And is when it's dependent on something. So count, like it is true if you have this and this, but not if it's only one of them.
Yeah, so this is all about truth tables. The AND is a logical operation that appears in every computer and basically answers yes if there are 2 inputs, yes and yes. Right, so it's a binary logical operation that has a truth value. So it has a truth table. A truth table for AND would look like this. So you say that this is the AND operation, and you have 2 inputs, and this input 1 and input 2. And they can have different values. They can have, one can, for example, be the input, say these are 2 statements, A and B. And the question is, what is the output of A and B if I wrote here 1 and 2, so maybe better to just write A and B. Is this my eraser? So if A is 1, oh, maybe I should put them here, and B is 1, then the output of the AND function is going to be 1. That's the same as saying if A is true and B is true, then the output of AND is true. 1 and 0, right? So let's go with true and false. But if A is false and B is true, you cannot say that both A and B are true. So AND is basically saying both are true, and so this is false. Similarly, if B is false and A is false, you would answer false. And if both are false, then for sure, if A is false and B is false, then C, like our conclusion, is false. So this is and is really easy to make. So if you have a neural network with 2 weights, this is your neuron 1 and this is your neuron 2 and this is your AND output neuron. You just have to select weights and a threshold that will get across only when both inputs are 2. So that's really easy, right? So if you have here, you take now the truth value and represent them by the binary values 1 and 0. In fact, integers because you can sum. Then if this guy is 1 and this guy is 1, then if we sum the 2 of them and make a threshold like larger or equal than 2, then your output will be 1. So threshold larger or equal than 2. Now, this is a very simple logical function written in a feed-forward neural network. There are other functions such as there's a great array of functions, but one of them is OR. And OR for A and B is true if either A or B are true, or both. So if A is true and B is true, OR responds true. If A or B are true, OR responds true as well. But if both are false, OR gives you a false. It's also easy to write one of these. You just lower the threshold a bit, right? You lower the threshold a bit, and you're gonna get that network letting all of the OR inputs pass. The big problem arrives when you need to write an XOR function. And the XOR function is a very fundamental function because it lets through only values. So true and true are not, okay. XOR means exclusive OR. Exclusive OR means both don't work. You have to have either one or the other. So basically it's the either or function, right? So true, true, and false, false give us falses. Whereas one true and the other one false returns true. The challenge is to write a feed-forward neural network with a single layer, selecting any weights that you want, that will encode here a function of XOR. Marvin Minsky and his great friend Papert, who was Seymour Papert, they wrote a book called Perceptrons, where they shown that the XOR function could not be performed by a feed-forward neural network with a single hidden layer, or without, basically, with a single layer. The book shattered the foundations of the by then growing idea of connectionism. Time went by, and eventually Marvin Minsky came to recant the importance of the book, because he then realized that ultimately, why do we care so much that you cannot do it with a single layer, since if you do it with two layers, that should give it to you. So I challenge you, for instance, to find here a hidden layer, a neural network with a hidden layer. Find these weights. So from 1 and 2 and 3 to 4, find weights such that when 1 and 0 or 0 and 1, you respond true, but when 1 and 1 or 0 and 0, you respond false. So that is the truth table you would like to have here. So the output, so if the inputs are this input 1 and 2, and outputs this should be the inputs are 1 and 2, and so the output. I'm writing the output on top. Might be actually better for you to understand if I'm put it on the bottom. But by now it's too late to change my notation. So
did you write down 3 as well? Because I can see the last
so
one.
You cannot see the screen. So the output is number 3. So this is output. So this maybe I should write it over here, output, which is number 3. Apologies. So didn't prepare this bit, so the notation is a bit off. Input 1, input 2, and here the output, which is number 4. No, I did not write number 3. Sorry. Who asked the question, Julian? No, I did not write number 3 because it's a bit of the challenge going on there. So question is find the weights such that this is the output function. I did not write what should be the activity of 3. But I can tell you, I can give you one hint. XOR is basically the OR function without the AND function. So whenever both of the inputs are active, you want to negate the output. So you wouldn't, if these two are summing together onto 3, then the output should be actually removing from the entire value. So you want number 3 to basically say no when 1 and 2 are on. So these would be positive weights, and this would be a negative weight. This is a possible XOR solving structure with a single hidden node. Can you find these weights, like just by manual tuning? That's a nice exercise for the next 15 minutes, because we are basically getting to the end of the first hour. I will leave this here, and you will find these weights: W13, W23, W14, W24, and W34. That solves the problem. Can you do that in 15 minutes? And then, if you, then we can reconvene in 15 minutes, and you can produce your answers onto the chat. Okay, Bill Friesen asked the question here that I have actually completely missed. I still don't quite understand why the threshold needs to be 2, and why 3 gives a false as a result. So now this relates to the earlier question. Actually, rephrasing, don't get how the threshold relates to dot product. A threshold is an extra operation. It doesn't relate directly to the dot product. Mace, you can also turn it around and make the middle node a NOR. Yeah, I mean, there are many ways you can actually solve the XOR problem, just as long as you get one intermediate neuron. So yes, Mace. Okay. Hold this thought. I mean, find the weights for the XOR. One more thing. Towards the end, so you have a little bit of a use of a dictionary, and that's nice. You learn about confusion matrix. Now you learn about the confusion matrix in a very intuitive fashion, right? So at the end here, you have a confusion matrix that doesn't have the stimuli that we had before. You basically have the stimuli that you want to categorize on the left, and you want a cat to be a cat, a dog to be a dog, and a rabbit to be a rabbit. But your neural network, because it makes errors, it doesn't manage to get it right every time. So the probability of the label being something given that the image is something else. So this is the notation here is in Bayesian probability notation. Could you construct one of these for your own network? So that's another something that is possible to pick up as a project for later. I will make available the projects as final projects, a suggestion for topics for the final projects later on today. But one of the projects that I wanted to suggest that someone that feels like starting in their great exploration in artificial neural networks is to look into the confusion matrix and relate it to the error functions such as the cross entropy category loss, which is a very relevant function in the space of artificial neural networks. Now, confusion matrix is something very intuitive to understand, and if cross entropy category loss sounds like a very hard, difficult, like almost unsurpassable set of words, where in fact they relate one-to-one to each other. So it is really nice then to try to bring this across to everybody else. How would we use a confusion matrix to compute the overall training loss or overall error of a neural network? This is not last time I'm going to be talking about neural networks. We're definitely going to be talking about supervised learning and training later on. And so that you can also then relate these concepts to gradient descent and so forth. But I wanted to introduce to you the idea of the confusion matrix as a way to quantify the amount of errors of the network. So this is just a description, and not only I hope that you can answer this question, according to the confusion matrix above, what is the most common mistake of the classifier? Can you answer this question? Could you answer this question?
A cat gets mistaken for a dog.
Cat gets mistaken for a dog most often. So you know that your stimuli, your cats and your dogs, as you're training them, might actually be too close for comfort, or indeed that your error or your supervision is not good enough. Your training set is probably off. But in any case, the point here is just simply to interpret it and to then create a confusion matrix for our own classifier. Any one of you guys like decided to get cracking on this particular question? Which is fine. It was a challenge. Every time you see a challenge in the projects, is something that you might want to pick up as a final project. Something relatively simple that we can then create a little bit of a spectrum around. So something that we can expand on. Create a confusion matrix and then potentially relate it to a cross entropy category loss. And then there is now one of our where did it go? To find out what this figure was. Oh, a neuron with a receptive field of 5 by 5 pixels. So the second aspect of this will appear one more time in our course, which is the idea of convolutions. When you have the receptive field for single neurons, the notion that you should have in the back of your mind is that your visual cortex is organized in such a way to detect lines and oriented bars across the entire visual field. So it is as if you have a zillion of these tiny little networks that locally are computing the orientation of the bars. You remember the slides from last week? So you have a map in your visual cortex that is selecting oriented bars, and the map is selecting oriented bars across the entire cortex. So you kind of have an array of these little tiny pre-processing stages. That is the fundamental idea behind convolutional neural networks. How many of you have ever heard the word convolution or convolutional neural networks? Can you answer in the chat, or maybe even better, like in Zoom, just give me the thumbs up or thumbs down in your figure. Just basically go into the reactions button and just say up or down. So yeah, that works, Ruth. So more people. So like I'm still expecting like a little bit of a poll here.
Does you saying it count?
No. Okay, so most of you have not heard about it, but you have definitely heard about deep learning. So in deep learning, the first stage of processing for every single network is a convolutional stage, where we in fact do this precise operation that I just described, where you create an array of recognizers, each of which looking into different parts of a picture. I mean, that is always the first stage of deep learning network. And we're going to get back to this point later on. But the idea here is that a convolution filter is applying a certain receptive field periodically over the entire picture. Now, if now you know how to write a 9×4 matrix, that would mean that you could also write a matrix of, say, 512 mapping onto, say, 512. Well, maybe I should take a different number. Say a network with 9 inputs, so 9 times, so and 810 input pixels to, say, 40 output pixels, where the 910 comes from a figure, and the 40 basically look into the orientation of bars, but each of which is mapping onto a specific bit of the input picture. That's the idea here that I try to convey in the filters and convolutions motivation paragraph, if you like. This is why, like in the learning goals, I have written that this sets the stage for things like the processing hierarchy, such as the increase of the receptive field complexity and receptive field size in multi-layer neural networks, which we will be talking about also in the lectures by Josh White. You will be able to explain the role of convolutional layers in image recognition. And in fact, you could probably even do it now. The idea is that you're pre-processing to extract some features, and you're doing this periodically over the entire input set. You will be able to, via the cross entropy category loss or any other error function, train a perceptron to recognize a set of patterns. And finally, look into backpropagation. So this project then has all of these many implications. We went through one step only to make it simple and easy, but the second step would be expanding on this. There's one here. Understanding the role of multiple layers in solving the XOR problem. So yeah, this is what I wanted to cover today with the review of the project. Any lingering questions? The opportunity with Elias can also help you there. If you have more, if you have them. The problem is at a very intuitive level, because I wanted you to be able to relate the code at a very low level to what's happening. Most of what happens nowadays in artificial intelligence is detaching the actual operations of the neural networks with the putting together of the network and engineering steps. So that's to say the APIs, the application interfaces for writing code for deep learning neural networks, such as TensorFlow or Theras, they are super complex, and they don't actually give you the access to the operations of the individual neurons, or the idea that you're building a small little stones and sticks network, which I think is a very valuable step up for everybody. So that's why this project exists in this form. If you have feedback or suggestions for the project, thank you, Felix, for spotting that slip. And I have nothing further to add. If you have no questions, let's take a 15-minute pause from 10 to 10:15. I will be here, so if you want to debate specifics, just let me know. And meanwhile, if you're feeling so inclined, you can try to find these weights for the XOR network, which are here. I'm going to stop the recording. Remind me to start it again before the next block.